All right, welcome everyone. I'm going to go ahead and get started today. Thank you for joining today's webinar. My name is Lisa Holmes and I'm the Marketing Director at Advanced Assembly. Today we are discussing designing with heavy copper. And this is actually a presentation Greg delivered at PCB West a couple weeks ago. But before we begin, I wanted to go over a few logistics. You should have a control panel on your screen. If you have any questions during the presentation, please use the chat box to ask them. We will try to answer the questions during the webinar, but we'll also have time for questions at the end. Now I'd like to go ahead and introduce our presenter, Greg Zeraldo. Greg is the Director of Operations at Advanced Assembly. With over 14 years of experience in PCB manufacturing, Greg is responsible for all areas of engineering and manufacturing at the company. Under his guidance, Advanced Assembly maintains a 98.8% on-time performance record, with orders shipping in 5 days or less on average. Prior to Advanced Assembly, Greg was Manager of Manufacturing at TTM Technologies. Now I'm going to go ahead and turn this over to Greg to get us started.
Good morning, everybody. Good afternoon to the people on the West Coast. Again, my name is Greg. Glad everybody could join. So this presentation is going to cover several facets of design and fabrication with heavy copper. Generally, heavy copper is considered at about 1.5 ounces per square foot. I want to talk about material properties, how to determine copper thickness for your designs, how manufacturers fabricate your board, and then challenges that we have when we are actually assembling it. Like Lisa said, at the end of the presentation, be glad to take questions. So if you have anything, write them down or feel free to use the chat box. If I could hit that in the middle of the presentation, I absolutely will. Let's get started. So copper has a few basic material properties that make it an excellent choice for electronics. And I want to kind of preface this discussion as this presentation is going to start really kind of at the entry level 101 class. And then we're going to kind of ramp up to a few more kind of technical key points that I want you guys to take away from this. But again, we're going to start basic and kind of go from there. So again, copper has excellent material properties that does make it the first choice for electronics. It has high electrical conductivity. It has a very high thermal conductivity. And it's also relatively inexpensive compared to other materials. Materials that conduct electrically well also tend to conduct heat well. Copper conducts heat and electricity better than any other common PCB material. It's perceived as better than aluminum, better than steel, better than gold. Silver is a slightly better thermal and electrical conductor than copper, but its cost is at least 100 times greater than copper's cost per pound. That really makes copper the primary conductor of heat on most PCBs. Designers will sometimes include aluminum heat sinks to help dissipate heat into the environment via convection, but that's really a choice based on based on cost. But at the end of the day, copper is the superior conductor. So we're going to go into some material properties. Copper and core material expand as the board temperature increases. The coefficient of the thermal expansion is really 1 to 2 orders of magnitude greater in the core layers than it is in the copper layers. So whenever the board changes temperatures, these two materials really expand at different rates. And materials can then experience mechanical stress. You can start inducing latent defects, immediate defects. Obviously, all these things need to be considered when you're designing. The glass fibers can strain in the expansion in the X and Y directions of the material, but the Z-axis expansion of the core materials is really where your trouble is going to set in. The core of the material can actually expand much more than the copper can. This is going to lead to a variety of failure modes and plated interconnects that will cause your board to fail somewhere down the road, as we discussed just a minute ago with latent defects. These failures are also not immediate. If they happen weeks or months at the end, this is ultimately going to lead into a failure. Speaking of failures, here's a couple of different examples of different via failures. If your plating isn't done correctly, your board is going to fail. When it comes to heavy copper, these images show cross sections of vias that are both post and mid failure. Via failures are not always an open circuit failure. Sometimes they will remain as a measurable resistance defect for a time before actually failing completely. Even if your plating is done correctly, high temperature thermal cycling in harsh environments can also cause your boards to fail as well. So I'm going to kind of go through a couple of these different images real quick. So this first image in this microsection is there are significant cracks and even cracks that are starting to propagate. On the left-hand side of the barrel, you see an entire fracture that's completely disconnecting. On the right-hand side, you start to see stress fractures going into that as well. So this can all be from heavy copper. This can be from high heat. This can be from mechanical stress. As I said a minute ago, what's going to happen with this is that you can obviously achieve an immediate open within that specific net. At the same time, too, the expanding and contracting of the copper as it goes through your thermal cycling can connect and disconnect all during the same test. It's going to throw your readings off. It's going to throw your basically all of your data off, resulting in failures. This second image right here is an entire fracture, where this would be a complete disconnect from the whole wall to the actual interconnect itself. And then this third image is a complete separation from the signal itself. So now that we've seen kind of a couple of different things of what thermal expansion can do with copper on the PCB, you probably realize that it's best to avoid large changes and rapid changes in temperature. What temperature change you decide is appropriate for your design is a matter of design requirements and the material properties of the core material that you choose. Some important laminate properties to consider when it comes to protecting circuit boards, especially from high temperature situations, include, I'm going to go over a couple of just key points here and some definitions that are really going to kind of help you in your journey as you go through this. So one of the first things that we typically look at is what we call TG, which is the glass transition temperature. And this is really the thermodynamic shift of the polymer of the core from rigid to soft. So basically when you are going through layup, your board is going through its pre cure. This is really at just what point the material becomes soft from rigid to soft, and then starts to actually flow. The z-axis expansion, this is the thermal expansion along the z-axis, and this is usually expressed as a percentage or CTE, which is a coefficient of thermal expansion. Next thing that we also look at is what we refer to as TD, or the decomposition temperature. The TD is the measurement of weight loss due to the resin degradation because of high heat. So it's that point of which 5% of the mass is lost due to decomposition. Next, we look at moisture absorption. This is actually how well a material can absorb moisture from the environment. And we'll talk about a couple of different materials that actually have significant problems if they're not addressed quickly with that. And then lastly that we look at is what we call time to delamination. And this is just basically the time delamination takes given at a certain temperature. Oh, slides are moving. Sorry about that. So standard materials that are pretty common in the PCB world, like 85N, FR4, 370HR, they all do well with heat. However, they're really heavy. So if you guys are designing for something that has a payload requirement, sometimes these need to be reviewed for consideration if the stack up is too large. 85NT is a laminate that actually uses aramid fibers as a base construction rather than woven glass. So this is going to support weight reduction and is very strong. However, it will absorb moisture very quickly and will require extensive pre-baking and vacuuming prior to post-lamination. So basically with this material, it's almost kind of like particle board if you're looking at like a wood reference. So instead of actual grains of wood, it's essentially fibers, almost looks like cardboard that's pressed together and bonded with resin. And what this material does is that it's incredibly strong. It's very, very lightweight, but it absorbs moisture like a sponge. So there is a significant amount of work that needs to be done in the inner layer stage, as well as the outer layer stages and sub-assemblies when you're manufacturing with 85 NT. So like I said a minute ago, vacuuming, pre-baking, post-baking are all things that need to be done to mitigate moisture in this, because what's going to happen is that you're going to go through, and especially if you're manufacturing heavy copper, high temperature in the HDI world, you're going to get to the final assembly of your build and you're going to have high resistance shorting all over the place. So just be careful with that. To conduct more heat and electricity with your PCB while keeping the temperature down, you must increase the cross-sectional area of your PCB trace. There's two ways to increase the cross-sectional area of the trace, and that's to increase the width or the thickness, or both. Increasing the width consumes valuable circuit board real estate, which leads to fewer boards per panel, which is ultimately going to increase your cost. Increasing the thickness of the traces increases production time a bit, but allows you to put more PCBs on a panel theoretically. The more PCBs per panel results in a lower production cost, and at the end of the day, that means money that you'll save. In theory, heavy copper also makes for a stronger board. Thicker copper helps to stiffen the boards, but you need to ask yourself, is this really what you need? So you know, I got a couple of different options to simulate these things. You have two that you can really use reliably. One of them is you can simulate or you can estimate. Estimation is really the cheapest, but it's really the least accurate option. It's more so with this is experience and time with the design is only going to be really useful here. If you're working with something that is brand new, a new type of technology that you guys are working with, this is not going to be a viable option. Simulation is going to involve software, sometimes hardware, but it's time consuming to set up and run, but it's going to really provide the best approximation for how your board is going to behave in the real world. Most modern design and CAM software platforms can really can run a conductor simulation for impedance values, either by Gerber layer or stack up. Typically what you can do on the, if you design a Gerber layer and there's a certain trace thickness, copper weight that you put in, you can essentially highlight that specific trace, that specific net, and kind of run a simulation test on how that is going to perform. Controlling impedance through dielectric and trace width and space needs to be considered for high frequency designs. As the designers, you guys can call out values in ohms with typically a plus or minus 10%, which is standard on these conductors. And the testing, of course, is going to be done what we call a TDR process, which is short for time domain reflectometry. If you are designing for harsh environments like high altitude, space, downhole locations where convection isn't available to cool your board, you should really simulate your design. Simulation is going to provide reasonably accurate information of how your board is going to behave in the real world. Tools that I prefer are SimScale, SolidWorks, Autodesk, Mentor. All of those things are going to provide a variety of simulation methods. And really what you choose depends on what you can budget and how accurate your simulation needs to be. If you depend on convection or forced air to cool your board, you might find that you need to choose a tool that can handle more of a fluid dynamics route. Otherwise, your data and your results are going to be inconclusive. They're not going to be accurate. If your budget doesn't allow for a fancy simulation software package, you're going to ultimately have to estimate, calculate, and calculate your trace thickness. Excuse me. Estimation is often good enough for simple designs if you can give yourself a suitable margin for error by derating your design based on expected operating conditions. A couple things to keep in mind is that if you guys are using the old equations from the IPC 2221 to calculate thickness and width, you can potentially be wasting a lot of copper, money, and time. I'm going to kind of go into some details with this, but I think it's really worth noting, especially since there is a perceived gospel of information that's out there that most design calculators use, but is not entirely accurate. I'm going to go into some details with that. So the equations from the IPC 2221 are derived from data that was formulated in 1956, actually, by a pair of pretty much unfunded researchers who really listed their results as tentative. The idea that an internal trace must be derated by 50% appears to come from an assumption in those charts, but not empirical evidence. It kind of turns out, just through our research for this talk, it was really wildly inaccurate. And internal traces can actually be derated as little as 5% in many cases. Those results somehow survived decades to be incorporated into formal standards and every single online calculator that we found when we were preparing for this talk. And it just, like I said a minute ago, it just really became gospel, even though there was nothing specific out there that actually confirmed or denied that these were actually accurate. IPC 2152 attempts to fix the problem with more recently derived data, but you don't need to purchase the standard to get the results and learn what the curves do. A couple gentlemen, Douglas Brooks and Johann Adam, wrote an entire book on the subject. And actually the most useful chapter of this book is actually free on Dr. Adam's website, and I'll post that here in a minute. You guys can take a look at that. If you're designing for a specific temperature change, that number becomes a constant. As your current increases, the trace width and/or thickness must also increase to compensate. Increased trace width does a slightly better job at dissipating heat than increased thickness. Back to Douglas Brooks's website is this UltraCAD URL that's posted at the bottom of this slide. And there's more details on that, and then issues with the original 2221, and really discuss at length how to use the new equations and curves from the newly derived IPC 2152. So in this graph right here, this is a couple of examples, and just really using the simple equation that I posted a minute ago on really kind of where this is going to be at. So this was simply arranged to provide clarity for a specific design temperature at an increase of 20 degrees C. So for a known current value that you guys have, this graph can really be used to determine trace width and copper weight. So for example, with this one is you have a 5 amp current that can be carried by a 430 mil wide trace at 1/4 ounce copper. By using the same method and equation, this would go down to, you could use a 130 mil wide 1 ounce trace, and then you could use a 40 mil wide 4 ounce copper trace. So remember that this assumes that this is unobstructed convection of surface traces at a standard temperature and atmospheric pressure. These equations are going to need to be reviewed if you guys are using space and downhole product applications. So when we talk about fabrication, so printed circuit boards are fabricated in dozens of steps. You can have basic circuit boards, 2-layer, 4-layer, that are built in 10 to 20 steps, and then you can have HDI and multi-lamination, microvia, copper fill that are 150 to 200 steps. The basic idea for internal layers is to remove copper in places that we don't want it to, through etching. The outer layers of copper are built up through electroplating, and then they're etched after that. So etching is used on the internal and external layers of PCBs to remove copper. So if your board stack-up requires 2 pieces of 2-ounce copper on internal layers, basically what the fab house is doing is going to be pulling out a sheet of 2-ounce copper clad material, and then just depending on your core substrate requirements. From there, the core is imaged and then is etched away with the copper remaining to actually create the pattern, or what we call artwork, and spaces of your PCB. From there, you're going to laminate those 2 sheets together in a press that is controlled by time, thermal rise, and cure, along with your outer layers. And then you're going to build up the outer layers and via holes with electroplating. Electroplating is used on the external layers of a PCB to add copper. So if your board stack up requires 2 3/4 ounces of copper, we're going to pull out a thin foil from our stack and then build up the copper on the surface and in the via holes to reach that 2 3/4 ounce per square foot of thickness. A couple of common issues that we run into on the fabrication side is that heavy copper is just honestly very, very difficult to fabricate. Whether it's etching internal layers that are heavy copper that are 2, 3, 4 ounce, 6 ounce, plated up, or anything that is on the outer layers that are significantly plated up. At the end of the day, etching can be one of the most difficult things to do. Anytime, at the end of the day, anytime something that's really difficult, fabricators are going to raise the cost of your boards as insurance against a lower yield. It's very common for boards to scrap due to over etching or under etching, for those panels to end up in the garbage, and ultimately they need to make sure that they're going to be recouping that cost, and so that cost is going to be pushed back to you. Heavy copper etching is often sometimes unreliable and time consuming. Boards can end up over etched on one side, like I mentioned, under etched on the other side. There's deep and narrow spaces that can trap etchant and keep fresh etchant from being applied. Plating is also very difficult, but for different reasons. An electroplated board doesn't always plate at the way that it's at right angles as far as on the board surface. Typically, especially with today's technology and plating, you need to go more of a pulse plating approach, which is using rectifiers and actual programs to be able to throw copper from the anodes onto the panel itself, rather than the old school way of using DC plating. At least with pulse plating, you're going to be getting more of an even layer of copper plating across the panel itself from edge to edge, as opposed to DC plating, where you typically build up heavier copper around the corners if you're not using thieving properly. Then after the boards are etched and plated, there's going to be other problems. Etched boards require a special high resin prepreg to fill the deep gaps and the voids that are created by etching. Basically with this, and we'll talk about this a little bit more as we get to the presentation, is that when you have heavy copper and you're etching, if you look at the Z-axis in a microsection, I kind of refer to the signal layers as they look like train tracks. And so on the internal side, if you're trying to fill those voids with prepreg, if you're not using enough of it, it's going to create voids, which ultimately at a microsection level is going to scrap your product. Once the boards have been laminated, the electroplated outer sides can be difficult to cover and solder mask, and then difficult to silkscreen as well. So just like on the inner layers where you have deep pockets to fill, the same thing goes on the outside. So if you were using a heavy copper outer layer, you might need more than one coat of solder mask to ensure that you have full copper encapsulation. Typically what can happen, especially if you're using a standard LPI or even a dry film solder mask on the outer layers, and you're only using one layer or one coat of that, you're going to get the deep pockets filled, but the crest or the crown of the trace is going to be extremely thin and are actually exposing the copper, which is going to result in either scrap or it's going to result in a significant amount of touch-up and rework. On the other side, if that you're using heavy copper on the outer layers and you do decide to go through a double pass with solder mask, you're ultimately increasing the thickness of your board too. So if you have a very tight restraint as far as what chassis the board is going into, you could be compromising that. Just something to think about. Assembly is the process of actually populating PCBs with your parts. This is referred to as populating, stuffing, assembling. It's got a multitude of different terms for it. Heavy copper PCBs, especially RoHS compliant PCBs, can be difficult to assemble due to the solder temperature required. So some issues that heavy copper PCBs have when it comes to assembly is that obviously heavy copper conducts heat a little bit too well. And essentially they act like a giant heat sink. They take much longer to heat up and much longer to cool down than regular boards. So this becomes a problem, especially if you're using higher technology parts. EGAs require a certain amount of ball collapse. The QFN packages require a certain amount of fillet, and voiding is allowed. So most people would think that you just do a simple change to a profile or slow the conveyor belts down through the reflow oven, and you assume that's no problem, right? Wrong. So now where we're at, we're really introducing more heat and really heating up the boards. And it's really at this point possible to cause the epoxy or fiberglass to decompose prematurely, like we talked about. And this is where vias can also experience some types of cracking and a host of other problems. Typically with a heavy copper and large layout board, there is a significant amount of preheat that is required, because ultimately what's going to happen with that is that you're going to have areas of cold solder if it's not done properly. So this all needs to be done through solder samples and, solder samples and your temperature profiling in your reflow oven. If this is something that you guys are going to be working on with heavy copper, you should probably be starting to have long conversations with your PCB manufacturers, engineering departments. Regardless of the size of your board, heavy copper is going to be a challenge really for anybody, depending on your design. And small, seemingly insignificant design decisions can lead to huge cost spikes. Again, like I said, latent defects or boards that just don't meet your design requirements. So I want to kind of go over a couple of things you guys want to keep in mind. So generally you want your layer stack to be symmetrical. So on a 4-layer board, if layer 1 is 2 ounce and layer 2 is 1 ounce, then layer 3 should be 1 ounce and layer 4 should be 2 ounce. This is really going to create a board with greater stability. If you have a board with uneven symmetry, it's going to have greater flexural strength on one side versus the other. And that means when the board heats up, as soon as it goes through, that finger. That means that when the board heats up, it's just going to flex cup. It could bow. I kind of alluded to looking like a Pringle chip. And there's a lot of criteria that, especially for aerospace, weapons, and defense, for flatness, for bow and twist. And if something is uneven copper weight, and especially heavy copper in that, it's not going to pass. It's ultimately going to be rejected in final QA. Next, I want to talk about crosshatch or cutouts to reduce your heat transfer. And this is kind of something that's a little bit interesting, and not everybody always thinks about this. An uninterrupted ground plane is always the top design goal, but sometimes it's necessary to prevent heat transfer to sensitive components. There's a couple of tricks that we can have when we're designing in our back pocket when we're working with high-end parts, such as precision voltage references. So first, you can use a hatched ground plane to reduce the rate of heat transfer to sensitive areas of the board. And this idea is used in wide areas of copper elsewhere, and that the heat will flow from hot components to cool areas and hopefully be dissipated there, leaving your sensitive part alone. So as you can see on this first image of this, Gerber artwork, so if you look next to the through holes on the left-hand side, instead of having a solid ground, you have a crosshatch pattern, which is ultimately going to, still create connections, still serve the purpose of the ground, but the crosshatch design is going to alleviate heat and dissipate heat much better. So secondly, this is kind of the fun one, and this is the one that I feel a lot of people kind of overlook. If you need to protect a really critical part, you can actually create a clearance and just make basically 3 to 4 sides around it using just enough copper to run your power and signal traces. So what you're seeing in the area that's arrowed is the white is obviously the clearance. And so the component that's going to be placed on that footprint right there, if there is a sensitive part to that component, you can clearance that, still maintaining total connection to the rest of the ground artwork, but you can leave that area free and clear so that that heat is not going to affect it. So I want to go over a couple of questions before we get into questions from the chat. And this is just a lot of common questions that we routinely see that might kind of clear up a few basic things for y'all before we get started on the next part. So one of the biggest things that we get asked is, how do I specify heavy copper in my stack up? Should I tell my fabricator that I want 2 ounce plated up to 3 ounce, or do I let the board shop decide? Of course, the easiest answer for that is going to be that completely depends on your board house. So we submit your fab drawing and your stack up that you want, unless you are ordering a board from Legacy Prints that specify precisely how the board is fabricated. Most of your fab houses today are going to have an array of off-the-shelf materials that are going to comply with the thickness that you require. However, older designs that ask for 2/2 material that's plated up to 4/4, ultimately this is just going to end up in additional steps that the fab process has to assume, and then ultimately it's just going to cost more. So being what I meant with that is that, I've seen drawings from the 90s, early 2000s that have their legacy designs. Typically these are DoD related, to where they want 2 ounce inner layers as a base material and they want them plated up to 4 ounce. Well, obviously now in today's world, 4 ounce copper layers is kind of common and they can be pulled off the shelf. But typically if you need something that's 2/2 that wants to get plated up to 4/4, there's a significant amount of processing that's involved with that. Not only the plating, but plating inner layers is very tedious, and then also actually etching those as well. So another question that we get to is discussions of embedding copper or using bus bars. And it's really, when would you recommend a bus bar or embedded copper instead of using heavy copper? So really what we talk about with this is really embedding anything into a PCB is going to add a significant amount of extra steps and therefore a significant cost. So I'd really avoid it if at all possible. I know a lot of people like to really design the hardest thing in the entire world to build. It's just kind of more of a proof of concept, but ultimately that doesn't add any value to the budget of the project. If you are designing a board that has 2 or 3 high current traces in it and everything else is low current, low voltage, high-speed digital traces that need controlled impedance, and you don't really have a choice, sometimes embedded copper or bus bars at that point is going to have to be required, but ultimately it just comes down to time and cost. Cycle time is going to be significantly added to these projects. So the one that we run a lot are, what is your minimum trace in space? And so this is a pretty generic detail of what fab companies are going to tell you. It's going to go over obviously your copper weights that are on the left-hand side. It's going to tell you what they're able to achieve for interlayer trace and spacing, external trace and spacing. But again, it also just depends on what type of equipment they have and just the general capabilities of the facility. We've seen people go down to 2 and 2. Obviously there's nanotechnology and micro etching that you can do to ensure that extremely small conductor widths and extremely small spacing can be achieved. It's just at the end of the day, it's going to be a conversation with your fab house on what they can do and certainly what they can't do. And obviously they need to be honest too and say, look, this is something that's out of our wheelhouse. I don't want to give you guys, expectations that we can and then ultimately fail. So as far as the presentation goes, that is the end of what we have. I'm going to start going through some questions.
Hi, this is Mark. I'd like to encourage you, if you have any questions, please ask Greg now. He's got a ton of experience and we've got plenty of time left to answer a few of those. So Greg, the first question we have is from an anonymous attendee. What is your opinion and or experience with epoxy resins, specifically for filling the gaps between heavy copper traces in a separate processing step?
So there's a multitude of different pre-pregs that are going to be used for that. As far as, specific call outs or on Isola materials or Arlon materials, is really anything off the shelf is going to be fine. It's really just a matter of actually how many pieces of pre-preg you're going to be putting in between them, and ultimately what your design goal is for what the copper weight is. It's really, again, going to be a conversation with your fab house and, telling them what you're trying to achieve and what they can do and what they recommend.
All right, we had a question in the chat window that I think you answered, but I'd like to add on to that if the commenter doesn't mind. When do you know, let's say you decide you need 3-ounce copper. When do you know that you need like a 1-ounce base, 2-ounce plate versus say a 2-ounce base and a 1-ounce plate?
So there's really not a scientific answer on why. It's really just personal preference. Again, in my experience, it comes down to the designer. At the end of the day, I mean, me personally, if it was up to me and I wanted a 3-ounce final thickness, I would just be pulling a 3-ounce copper clad piece of material. But again, there are older designs and some people design them where they want a base that's plated up. But again, at the end of the day, if copper thickness is what you're trying to achieve, then it's best to use that clad material right off the shelf, because plating up, if it's not done correctly, there's going to be like a demarcation line between the base copper and what's been plated up. There's a risk for more fracturing at that level if it's not been prepped and plated properly. There's just a host of other issues that kind of come along with it. And from a risk mitigation standpoint, I would just prefer to go with the original clad material at the thickness that you need.
All right, what other questions do we have out there from TV land? Ask them now, or you'll have to get back to work. All right, from Howard Evans, we've got Gray Beards used to tell me that plated copper was not as thermally conductive as clad, annealed copper. Recently, I've read this is not true. So I think the question is, do you have any knowledge on that, on the thermal conductivity differences for?
That's a really good question. I've been a gray beard myself. I don't I don't think I've actually ever heard one versus the other. I think it's one of the, to me, I don't know if that's an old wives' tale or what. Obviously, plated copper, if you look at it more at the microscopic level, the grains are slightly different than clad material. But as far as it actually being able to have a measurable difference in how it transfers heat and conducts heat, I have yet to see anything that proves or disproves that one is better than the other. Again, I think, going back to the graybeard comment, you're going to have people who are, I guess, more old school that are used to doing it one way. And then newer processes, equipment, and data has supported that things are not necessarily what they seem. So it's one of those things where you got to take it with a grain of salt and just don't take it for face value. But I have yet to see anything in the industry, whether it's publishings, white papers, or anything like that, that show that one is truly better than the other.
And to answer that too, Howard, from a physics standpoint, I can't imagine that the difference would be so great that you would be able to measure it in anything other than a controlled laboratory environment. For all practical purposes on a circuit board, maybe you're looking at the change of maybe 0.1%, but copper's got a thermal conductivity of 430 watts per meter Kelvin. Are we talking about 430 versus 430.02? It would have no practical difference, because once you get to the air interface, you're looking at like a 0.02 watts per meter Kelvin. It's a 2 to 3 order of magnitude difference. I just can't imagine that it would be meaningful in any sense at all from the physics and the material standpoint.
Agreed.
All right, from Kelly Minton, what size vias can be drilled and plated with 2-ounce or greater copper? So what about via size when we're doing heavy copper?
Via size is obviously, via size is going to be critical when you're dealing with heavy copper. Micro vias are completely out of the question. And your standard mechanical drill size of 7, 10, 11 mils, even those are going to get extremely dicey, because at that point you're throwing thousands of basically mils of copper onto the internal hole wall. I really wouldn't touch anything that's under 10 mils.
All right. Hopefully that answers Kelly's question. If not, please feel free to follow up. What about cost, Greg? If I'm designing with heavy copper, is it cheaper if I use all external heavy copper, all internal, a mixture? What can I do to see cost savings with this technique?
The biggest thing with heavy copper from a cost saving standpoint is really making sure that your stack up, you're able to use as much off the shelf material as you possibly can. Because, you know, like we had talked about it in the presentation and even just a few minutes ago, is that if you are actually using a base material and then plating up or doing a significant amount of plating on the external layers, all of those are more process. They could be more drill cycles. Ultimately, if you have typically in heavy copper, there's going to be separated drill from the vias to the actual plated through holes, to where there's different plating steps, there's different imaging steps. And so as much of those as you can reduce, the steps that you can reduce, it's ultimately going to be a cost savings. Unfortunately, cost savings and heavy copper are kind of the antithesis of each other. So you're not out of the gate, you kind of have to expect that you're going to be paying a little bit more for it than a standard process of, you know, 1/2 ounce or 1 ounce or standard 1 mil plating in the hole and everything like that. But there are certain ways, like I said, with off the shelf materials and things that are readily available to you before you start going the custom route. Custom's never cheap.
All right, what else would you guys like to know? We've answered all questions. Okay, then I'll continue to ask some unless the community would like to join in. What about custom reflow profiles? Advanced assembly, I think you guys have some ovens that allow some targeted temperature measurement and very quick custom reflow generation. Can you tell us a little bit about how that works?
So at Advanced Assembly, we actually have 2 different ways that we reflow, or 2 different capabilities of reflow. So we have conventional reflow, which I refer to as basically your standard conveyorized pizza oven with a multitude of different heating zones and cooling zones for reflow. One of the actual, you know, and these work great for a multitude of different industries and different types of designs, because we can change that profile to do a quicker and higher pre-soak prior to the reflow point. So that way, you know, from a thermal standpoint, you're not putting too much initial thermal stress on the board when it goes through the reflow zone. The other thing that we also have available to us too is what is referred to as vapor phase reflow, which is not nitrogen reflow. And so there's a few manufacturers out there that use it, but we use it regularly and we love it. And basically what it's actually using, instead of heat zones, it's using actually a chemical conversion to create heat and vacuum inside of a sealed chamber. So from a thermal standpoint with heavy copper, it reduces the ability for the board to be used as a heat sink, and more just, again, as a carrier for the parts. So once this chemical conversion happens in this chamber, it immediately creates the appropriate amount of heat for the board itself, and then the vacuum actually pulls the part down onto the footprint. So from a voiding standpoint, especially that is rampant with high heat and heavy copper, from a standard conventional reflow, we were able to see 90-95% void-free bottom terminal leadless parts. Highly recommended.
All right. Well, with that, perhaps we can bring Lisa back. And are you there, Lisa?
I will. Yep, I'm here. So we will go ahead and wrap it up for now. If there is anything that you think of that you would like to ask Greg, we will be emailing a recording of today's presentation along with his contact information. So you can please feel free to reach out to him with any further questions. And so thank you everyone for joining us today, and we will see you next time.
And Kelly and Lou, I do see your questions. We'll get the answers for that to you. Thanks.
All right. Sounds great. Thanks everyone.